wondered how moisture in the air influences the weather we experience? Well, buckle up because we're about to embark on a whirlwind journey through the intriguing world of weather and moisture. Moisture, the unsung hero of weather phenomena, can exist in three states: solid, liquid, and gas. The gaseous form of moisture, known as water vapor, plays a pivotal role in weather patterns. When air becomes saturated with water vapor, we reach a turning point called saturation. It's at this juncture that a fascinating process called condensation takes place, where water vapor transforms back into liquid. The result? A meteorological spectacle featuring clouds, rain, fog, and snow, all products of condensation. But what triggers saturation? It's all about the temperature. The air holds as much water vapor as it can at its current temperature. Once this threshold is met, we've reached the dew point, the temperature at which air becomes saturated with water vapor. And here's a little nugget of wisdom. The dew point isn't static. It dances to the rhythm of the day, changing based on the moisture in the air. Now let's stir humidity into the mix. When we talk about humidity, we're referring to relative humidity, which is the amount of moisture in the air compared to its total water vapor capacity at a specific temperature, expressed as a percentage. The higher the percentage, the more humid it feels. Let's shift gears to a specific form of condensation: fog. Think of fog as a cloud that's decided to take a scenic ground-level tour. It forms when the temperature and dew point are close, and the winds are light. Understanding condensation is the first step in understanding the weather around us. This journey through the world of weather and moisture is just the beginning. As we continue to explore, we'll uncover more about the dew point, humidity, fog, and other fascinating weather phenomena. So stay tuned, and let's unravel the mysteries of the skies together. So, what happens when air becomes saturated with water vapor? This question leads us into the intriguing world of dew points and humidity. Let's break it down. The dew point is the temperature at which air becomes saturated with water vapor. Once the air temperature drops to the dew point, the moisture starts to condense out of the air, forming dew or frost. Interestingly, the dew point is not a fixed value. It shifts throughout the day, influenced by the fluctuating moisture levels in the air. Now, how about humidity? When we talk about humidity, we're referring to the concept of relative humidity. Relative humidity is a percentage that measures the current absolute humidity against the highest possible absolute humidity, which would occur if the air were saturated. Essentially, it's how close the air is to being completely filled with water vapor at a specific temperature. To illustrate, imagine you're in a desert. The air might hold a small amount of water vapor, but because the temperature is so high, the air could potentially hold much more. So, even though you're surrounded by dry air, the relative humidity could be quite low, say 10%. Conversely, in a cool, damp forest, the air might be nearly saturated with moisture, so the relative humidity could be up to 90%. Relative humidity is a crucial factor in weather conditions. It influences the formation of clouds, fog, dew, and precipitation. For example, when the relative humidity reaches 100%, the air is saturated, and the excess moisture can condense into droplets, forming clouds or fog. On a hot, humid day, you might hear someone say, "It's not the heat, it's the humidity." And there is some truth to that. High relative humidity can make hot temperatures feel even hotter because it slows down the evaporation of sweat, our body's natural cooling mechanism. So there you have it. Humidity is more than just a measure of how stuffy it feels outside. It's a key player in the weather game. It's time to give this unsung hero the recognition it deserves. Have you ever wondered what fog really is? Just like clouds and dew, fog is a form of condensation. But unlike its high-flying counterparts, fog likes to keep things low-key, hugging the ground closely. Think of it as a cloud that's decided to visit us at ground level. Now, for our friendly fog to form, we need a few specific conditions. First, the air temperature and dew point need to be close together, usually within about 4 degrees of each other. This closeness allows the air to become saturated with water vapor, leading to condensation. Second, we need light winds. If the winds get too gusty, they'll disperse the fog, and our ground-level cloud disappears. So, the next time you find yourself in a thick fog, remember that you're basically walking through a cloud. Fog, the mysterious cloud on the ground, is simply another marvel of nature. Now, let's talk about something we all experience: precipitation. Precipitation is essentially Mother Nature's way of recycling water. It's the process where water vapor in the atmosphere condenses into droplets and falls to the Earth's surface. We're familiar with its most common forms: rain, snow, and ice, but it can also appear as sleet or hail. Precipitation is more than just an umbrella or a snowball fight. It's a vital element of our planet's water cycle, replenishing our water sources and nourishing our vegetation. It also plays a key role in determining our climate and weather patterns. But let's not forget, precipitation can also present challenges, particularly when it comes to visibility. Ever tried driving in a heavy downpour or a blizzard? It's not the easiest, is it? The same applies to pilots. The harder it rains, the more it reduces visibility, making flying conditions difficult. And what about runways? Much like roads, runways can be significantly affected by precipitation. Rain, for example, can make runways slippery, posing a risk during takeoff and landing. Snow and ice, on the other hand, can cause runways to be temporarily closed until they're cleared. Whether it's a drizzle or a downpour, precipitation plays a critical role in our weather. It's a constant reminder of the dynamic and ever-changing world of weather that surrounds us. Now, what about the challenges that come with freezing rain and ice? Indeed, ice is not just a nuisance for your morning commute, but a formidable foe for aircraft and runways. Icing conditions can lead to a buildup of ice on aircraft wings, reducing lift and increasing drag. This, in turn, can hamper a plane's performance and even lead to engine failure. On the ground, icy runways make takeoffs and landings a slippery affair, often requiring the use of specialized de-icing equipment. But how does all this moisture end up in the atmosphere in the first place? Enter the water cycle, the Earth's very own recycling system. This continuous process is driven by the heat of the sun, causing water to evaporate from the Earth's surface. This water vapor then ascends into the atmosphere, where it cools and condenses to form clouds. Clouds are more than just fluffy, white decorations in the sky. They play a crucial role in the water cycle, acting as the stage for the next act: precipitation. When the cloud droplets become too heavy to float in the air, they fall back to the Earth as rain, snow, or even ice, depending on the temperature. So, from a tiny droplet evaporating from a leaf to a giant thundercloud releasing a downpour, every stage of the water cycle is a vital part of our weather system. From a tiny ice crystal to an enormous cloud, every stage of the water cycle contributes to our weather. Clouds are more than just pretty shapes in the sky. They're the key to understanding weather patterns and predicting atmospheric changes. Each cloud tells a tale of its own, providing clues about the weather to come. Let's consider cumulus clouds, those fluffy, cotton candy-like formations that often remind us of fair weather. But don't let their charming appearance fool you. These clouds are also harbingers of turbulence. You see, cumulus clouds are formed by strong updrafts of warm, moist air. These updrafts produce turbulence in the sky, turning a seemingly smooth flight into a bumpy ride. So why are cumulus clouds turbulent? It's all about the air. As warm air rises and cools, it forms these clouds. The constant movement of air within these clouds results in turbulence. So, the next time you see a cumulus cloud, remember, it's not just a pretty face. It's a sign of the atmospheric drama unfolding above. Clouds are the storytellers of the sky, and understanding them can help us predict the weather. Not all clouds are created equal. Indeed, the sky is a canvas painted with a myriad of cloud types, each with its own unique characteristics. Our cloud classification begins with height and appearance. High-level clouds, such as the wispy cirrus, form above 20,000 feet and are composed of ice crystals, often painting a delicate lacework across the sky. Moving down the atmospheric layers, we find mid-level clouds like alto stratus and alto cumulus, hovering between 6,500 and 20,000 feet. These clouds often blanket the sky, creating a uniform gray appearance. Closer to the ground, below 6,500 feet, we encounter low-level clouds like stratus and cumulus. These are the clouds we're most familiar with. the fluffy cumulus that bring fair weather and the flat stratus that often bring rain or snow. Lastly, let's not forget the unique lenticular clouds, their lens-like shape forming at high altitudes, often near mountain ranges. While they indicate turbulence, for glider pilots, they're a sign of smooth, strong lift. From fluffy cumulus to wispy cirrus, each cloud brings its own weather story.